Welcome to the ChemDoctor, and what I'd like to do in this presentation is teach the viewer how to calculate the pH and concentration of sulfite ion in a 2 molar solution of sulfurous acid. Now, the reason why I want to take the time to do this presentation is because, first off, sulfurous acid is a polyprotic acid, so its ionization occurs in two steps because a polyprotic acid contains more than one proton. So we see for the first ionization that sulfurous acid is going to ionize into hydronium ion plus hydrogen sulfite. All right, and this has a Ka value. We'll call it Ka1 of 0.016. All right, and then in the second step, the hydrogen sulfite ionizes to form another mole of H3O plus, and ultimately the sulfite anion. All right, so in this problem, what we want to do is we want to calculate the concentration of the SO3 minus 2, and we want to calculate the pH of the solution. And oh yes, the equilibrium constant for the second step here is equal to 6.4 times 10 to the minus 8th. Now, I would highly recommend to the viewer that you've seen my other presentations on solving for the pH of a weak acid, for the pH of a weak base, solving for the pH of a mixture of weak acids, and also I have other video presentations on polyprotic acids. The reason that we're focusing on this one, or that I'm making a special presentation on it, is because what we're going to see is that in the first step of this reaction, our K constant is large, and as a result, since we want the pH of this solution, we're going to find out that this particular acid violates the 5% rule if we neglect X in the first step. So let's very quickly go through and calculate for the concentration of hydronium using the standard methods that we normally use when we're solving for the pH of a weak acid problem. So we're going to set up an ICE table. In my class I call this a before-after. So before we've actually made the solution, we're going to have what will amount to our initial concentration of the weak acid, but we will have no production of the H3O plus or the hydrogen sulfite ion. Once we splash the acid into water to make the solution, then our system is going to change and shift in order to reach equilibrium. And in that process, our 2 molar is going to decrease by X based on the stoichiometry of the reaction. The hydronium will be produced by X, and the hydrogen sulfite will also be produced by the same amount, since there's a coefficient of 1 in both cases here. Now our equilibrium expression for this, the way we would set this up is it's going to be X times X over 2 molar minus X, and the whole thing is equal to the equilibrium constant, which is 0.016. Now normally, and out of the gate, you would go ahead and neglect the X here, and so I'll just cross this out. And then you would solve for X. So X squared is going to equal 2 times 0.016, just doing the algebra. And so our X value, where we take the square root of this, would equal 0.179 molar. Now, I'm not going to actually calculate the pH using this value, and the reason I'm not is because the main point of this video is to show you that if we've neglected the X and we check our 5% rule, which is the same as calculating the percent dissociation, this is going to equal 0.179 divided by 2 times 100. And when you run that calculation, what you're going to see is that we're approximately at 9%. So what that means is that it was not valid to neglect the X in this. And so we cannot actually calculate the pH with this. And that's the whole point of this presentation. So what do we do? All right. So what we're going to need to do ultimately to find the pH is use the quadratic formula. All right. And so we're going to go back to this expression right here. I'll go ahead and rewrite it. So we're going to have X squared over 2 molar minus X. The whole thing is equal to 0.016. Now, when we convert this over and get a binomial equation, it's going to look like this, where X squared, it'll be X squared plus 0.016X minus 0.032, and the whole thing is set equal to 0. So I am not actually going to write down the quadratic formula here. Most graphing calculators can be programmed for this. If the viewer is not sure what I did to solve for X, which will happen in the next step, go pause the video, go to Wikipedia, and extract that equation. What it's going to look like when we insert everything into it will be this. So we're going to have minus 0.016 plus or minus the square root of. All right, and then we're going to have underneath the square root 0.016 quantity squared minus 4 times A, which is 1, and then times C, which is a minus 0.032. And then the whole thing is over 2 times A, which is 1. And so when you do this, some viewers are also going to be concerned because we're going to get 2 answers here. But you got to use common sense. Only one of the answers is going to work. And the answer that works is going to be 0.171. In the other case, you're going to get a negative value, and you're not going to have a negative concentration. So it's this quantity right here that actually equals our H3O+. All right, and it also equals the hydrogen sulfite. If you plug this value back in like we did for the 5% rule, yeah, it's going to violate. That's how come we use the quadratic to actually calculate this. It's the only accurate way to get a handle on this concentration. So we would calculate now the pH from this. All right, and so the pH is going to be equal to minus the log, and it'll be concentration 0.171. And when we do that, we get a pH for this particular solution that's going to be 0.77. It's a pretty high pH. It should be, because note that the equilibrium constant for this weak acid is pretty large for the first step. Now, in order to find the sulfite, all right, we have to run the second step of this reaction. Let me just fix that up a little bit. All right, and so to do that, now you need to recognize that we have a common ion. The other thing is that the equilibrium constant is small for this. It's 10 to the minus 8th. So in the second step of this, we're going to go ahead and neglect the X. And I'll show the viewer at the end that it was okay to make that assumption. But like I said, we have a common ion issue now because here's the concentration of the hydronium and the sulfite ion. So for this ICE table, we're starting out with 0.171 molar of the hydrogen sulfite and 0.171 molar of the hydronium and 0 of the sulfite. When our system comes to equilibrium, it'll be 0.171 minus X for this, 0.171 plus X for this guy, and X for this guy. So when we set up our equilibrium expression, it's going to be X. Now I'm going to go ahead and neglect my X's in the sum. So for this guy, it's going to be 0.171 molar divided by this guy, so it'll be 0.171 molar. And we see There's a lesson here that I've talked about in previous videos. We see that for the second step of the polyprotic, the concentration of the anion is literally equal to the equilibrium constant for that step. See, these guys cancel out as long as we're able to neglect the x values. So our x value, which equals the sulfite ion, is equal to 6.4 times 10 to the minus 8th molar. All right, now you can check this thing if you're skeptical about having dropped the x. So we can just run the 5% rule really quick, and it's going to be 6.4 times 10 to the minus 8th divided by 0.171 times 100, and what you're going to get is a really small value here. I think it's about 3.7 times 10 to the minus 7th percent, literally. So that means it was valid for us to go ahead and drop the x out of this sum. Alright, so with that, I'd like to go ahead and close the video. I'd like to thank the viewer for coming to ChemDoctor for help. Please see more videos at www.chemdoctor.org. Have a good day, and I hope that this helped you with some chemistry. Alright, and we'll see you on the flip-flop.